very much. It's really good to be here. I'm Jonathan Smith. I'm a solution area expert at Net Insights, so mostly focused on the use of, let's say, cloud technology for transport, especially focused around the sports arena. But today I'm going to talk a little bit about the need to focus on efficiency, and a little bit about why that's crucially important to us at the moment. So there's a lot of pressure on our industry at the moment, and in the good old days when I started my career 20 and a bit years ago, I know I look too young, right? No? Okay. It was all quite straightforward. We took a few camera feeds, we connected them to a production system, we contributed them to the places they need to be, we did a bit of playout, and our consumers were mostly chained to TV screens, which was great because there wasn't any problem with trying to drive engagement. Either you were watching the TV or you weren't, and we could drive adverts at them effectively, and it was all very straightforward. And then along came some kind of pressure. So the consumers themselves started to have access to different platforms, mobiles, OTT platforms, social media. They became a more fickle group of consumers. They're able to now consume content in lots of different places. They're no longer chained to a television. And so now as a broadcast business, we end up needing to focus more on content creation and monetization and engagement. And that means doing more stuff. So I need to make more streams. I need to think about how I create different engagement opportunities. So second screen, alternate angles, player cameras, all of these additional bits of work we're trying to do and pipeline through this chain. And so suddenly the bit in the middle starts to have more of an efficiency need to be able to do all this stuff. And we kind of responded. I think many years ago we were content that CDN IP platforms would provide a delivery mechanism to all of those connected edge devices. We went through a transition to be able to do playout services in the cloud, and if you look at any fast channel, and most broadcasters now have playout presence within cloud services. And then, of course, remote and cloud production. And all of these services share the opportunity to have a kind of ubiquitous connectivity. And that one ubiquitous piece of connectivity are unmanaged IP networks and internet delivery. Not saying it's all done there today, but that is the obvious place where there is a technology that we can use. We can use IP, we can use internet for connectivity across all of these different areas in our chain. Interestingly, with some of the requirements in acquisition, if you like, of signals, we're still seeing a lot of fiber being used for high bit rates, JPEG XS, uncompressed, low latency feeds from venue to production. But generally, this is the picture we're now seeing. So if I divide this down a bit more and look at some of the data, the way that content is being moved is also changing. Now, this is a global kind of bit of data pulled from Coretta. It's skewed slightly for the North American market, where satellite for primary distribution is still quite commonly used for affiliates, where you're doing 1 to hundreds. It's an efficient way of doing it still. But the overall picture is interesting, and it's consistent across the globe that internet and IP delivery is the most rapidly increasing area of transport among us. And the interesting thing as well is the overall market size is also increasing. But the overall market size isn't increasing in line with the same amount of streams that are being delivered. We're doing more, we're creating more, and we're sending more to our consumers. And our market size is slowly increasing. And that tells us one thing. That tells us that the cost per stream to be delivered is actually, or required, is going down. And so we need to be kind of laser focused on efficiency. So if we take a look at our value chain, and we break it down a little bit more. So, everyone will be familiar with this: venue transport, production services, contribution transport, localization, and primary distribution. And these blocks aren't all created equal, let's say. So if we look at that chain today and break it up a little bit, I want to talk a bit about what we should be doing where in this chain. So I think we can probably pluck it apart like this, and the blue boxes there I look at as being potential areas for value addition to our content. These are actual opportunities for you to use technology, to use features, to add more value to the content that you've acquired. In production, of course, we have talented directors and producers and operators that that are creating, graphical experiences. They're creating punchy editing. They're the marketeers of our content as it arrives. And then in localization, we're creating, more focused personalities for our content that's more appropriate to the different demographics that are going to be receiving them, whether that's personalization through ads or regionalization through language or captioning and so on. And these are areas that require new features. These are areas that maybe things like AI, machine learning, and stuff like that can add real agility to what we're trying to do and bring value to the market. But in transport, we're the plumbing, right? We're connecting services together, and we don't really add value. We can detract value in a heartbeat. If we're unreliable, if we're not scalable, and if we're not efficient, then we can destroy quite easily any monetization opportunity with content. And so then our focus has to be a little different. We have to think about reliability. We have to think about the ability to provide scalable transport solutions, and of course, most importantly, efficiency in that plumbing we're providing. So I thought I'd take a look at reliable internet transport, and I've come up with a 4-step program. This is popular amongst various walks in life. And so the first step is that you pick an ARQ protocol. So that allows you to deliver stuff over the internet reliably, of course, and we can talk about which one's the best. I'm sure I'll be asked. You pick a gateway vendor, right? You need a box to plug something into, some IP or some SDI or some ASI. So pick a gateway vendor. I won't tell you which one of those is the best. And you make a connection over the internet. And then once you've done that, you bask in the glory of cost-effective media transport. So it's very straightforward, and I resisted drawing a cloud for the internet, so I hope you're pleased with that as well. And so this is how we got started. When internet delivery was the focus of, let's say, Tier 3, Tier 2 sports broadcasting, then you wanted a cost-effective encoder, a cost-effective decoder, and you plug them together. You use the internet as the transport mechanism because it's very cost-effective for moving stuff around. And that's great, right? So this is how we started. But we really need to dig into reliability a little bit more and move beyond the transport protocol. So that ARQ protocol is there to enable a lossy network to be used for transporting real-time video. But there's so much more to creating reliability end-to-end in this process. So one of the problems with bolting boxes together over the internet is we get absolutely awful observability. If you think about any internet connection between two places, you'll have first-mile transport through some chosen ISP. They'll be peering across the core of the internet and some last-mile delivery through another local ISP to the destination. And if we just bolt boxes together, we end up with kind of a binary observation. We're saying, okay, it looks good to me, or it doesn't look good to me. It's either working or it's not. And your ability to understand kind of that black hole of routing across the internet is very, very limited. And you're going to be having weird conversations. And everyone that's worked in service provision or at broadcasters will understand the conversation about demarcation, the responsibility. Whose problem is this? I'm handing off to a partner at the right-hand side, and all I know is the signal's not making it there. Well, who's responsible for that? Is it their system? Is it my system? And with this binary kind of observation, you can't make any of those decisions. And that gets very difficult when you're trying to operate in more of a tier 1 kind of service provision, trying to hit difficult and complicated SLAs and meet those requirements. So we have to kind of think a little differently. And if we throw away boxes and we just start talking about nodes, then nodes, and this is kind of how we think about our networks. Our networks are completely software-defined networks. We use containers to be able to deploy them, whether that's a piece of encoding hardware or whether that's in AWS or whether that's in any bit of COTS resource. We can deploy that anywhere. And the reason we do that is so you can have a point of presence across your network, and you can demark the network effectively based on your needs. So once we try to break down this transport, then we can put these probes, we can put these points of presence at the handoff, at the region that allows you to see that first mile, and do the same on the last mile. And so we can build networks now that are completely software defined, that have observability built into them. So every node we deploy has all the transport stream data, it has all the IP metrics and data, and that's all brought up into an observability layer that allows us to understand where exactly things are going wrong, or potentially going wrong in our transport. We can take that model and apply some good old-fashioned broadcast resilience engineering, delivering to two places, picking diverse ISPs. And the more complex that gets, the more orchestration is important across this. So when we look at this, if I tried doing this with boxes, I probably wouldn't bother, because I've got to bolt one box to the next box, to the next box, to the next box. I've got to configure all of those hops one by one, point to point, every time. And this would just be operationally problematic for me. And what I'd save in robustness and reliability, I've detracted in the need for me to throw more people at the problem and more configuration at the problem. So the other thing we firmly believe in is that orchestration end-to-end across any software-defined network is of crucial importance to making sure we're being efficient and reliable in the way we're delivering transport. So I think next I want to talk a little bit about efficiency. And efficiency in that transport layer. And certainly, not all transport implementations are created equal. And I'll talk a little bit about what we need to be focused on. And sometimes it's the focus on the boring things that bring the best results. And that's not flashy, that's not very good for our marketing team, but actually for our customers right now, efficiency is the thing we can do to help the industry. And so that's why we're kind of laser focused on this at the moment. So this is my second 4-step program of the day. If you need any more, let me know. So you pick an ARQ protocol. You notice this is a common theme. And once you've done that, you grab the example application or the library, in order to do something with it. And you integrate that into your core application. You grab you grab RIST or you grab libsrt and you integrate it into your application. It's great. It comes fully packaged. It's ready to go. You just make some connectors and you've got software. So then you bask in the glory of rapid transport protocol integration. This is straightforward, right? Now I've got a fully integrated ARQ protocol into my boxes, and off I go. I've got a product. I can sell it. Brilliant. Then the phone rings. Who's on the phone? It's my customer. We're not getting very good throughput per node. I say, brilliant. Let me put you through to the sales team. We can sell you more nodes. And the customer thinks about that and makes grumpy customer noises. Because, of course, people don't want to spend more money on more nodes. They want to have more throughput per node. And so then we kind of go, okay, well, we've got support for all of these ARQ protocols, but for some reason the industry isn't happy with the amount we can do with it. And so we had to take the kind of step, I guess, to completely roll our own implementation from scratch. Understanding the very core principles of these protocols, but being able to create our own application layer that deals with them. And some features, some efficiency features are inbuilt. So RIST, for example, has got a great stream muxing feature. So if I use stream muxing, I can take this picture where I've got transmitters and receivers, and all my streams are sent inside the RIST protocol with my transport stream happily protected. And each one of these send acknowledgements, or in the case of RIST, not acknowledgements, but all of the ARQ protocols have some kind of handshaking, of course, to be able to go and ask for the missing packets. And each one of these connections then has overhead. It has this encapsulation overhead that is there for the communication. So what we can do is say, okay, well, a more efficient way of dealing with this is by muxing all my transport streams inside one tunnel, and that tunnel is then only needs one measurement of overhead to provide the handshaking back and forth across the network. So this is in theory, a more efficient way of doing this. Great. So everyone just goes and muxes all the streams into each tunnel they need to, and I get highly efficient ARQ transport. But it's not as simple, unfortunately, as it seems. So if I just take those example libraries and I use them, then what I'll find is that I've got a resource utilization problem, because every time I implement a transmit or a receive, then another thread will be spun out of that, that example application. And in the left-hand side, where I've got one of these threads for every single thing I'm doing, by the very nature of the OSs we're running on, they'll probably go and do a good job about sending them to different CPUs. If I do the stream muxing thing, I'm going to make one thread, and I'm going to go to one CPU, and I'm going to fill up that CPU, and I'm probably running on some kind of node that might have 10, 20, 30 CPUs available to me. And so then I've got a problem. And so the only real way of doing this is by rolling your own implementation. So what we've had to do then is take all of these, these example libraries, we look at the protocols and we understand them, and actually what we do is a combination of, let me go back one. A combination of both of these, where we're using stream muxing where appropriate. So we look at the topology of the network. We work out all the kind of logical tunnels that are needed across the steps in the network. Then we mux as many streams as needed automatically into each of those tunnels. But where we need to load balance, we're then taking that single transport layer, the single receive or send, and we load balance that explicitly, that one process across, by making it sub-processes across the CPUs. So actually we do a couple of things when we do that. We look at that single kind of application performance and we load balance that across CPUs. But because we're container-based, we can also distribute those points of presence, those regional nodes, if you like, across multiple hosts. And so then the system, the orchestration, will also load balance these connections across nodes as well. So suddenly now I have scalability and efficiency in both that base protocol and also the kind of the topology of my network. So we really have to you have to dig deeper to really make this fly. And so some examples, like I won't talk about competitors, of course, but I'll just tell you where we've come. We've come on a journey. So we, hopefully there'll be a cheer here. We use RIST for all of our internal, let's say, network communications. So once at the edge of the network, we're agnostic to the input or the handoff. But in that kind of topology of our network, we use RIST explicitly because we found it to be more efficient, certainly in our implementation. And so we are always a container-based deployment. There are a couple of different ways of doing it. Sometimes we use a Kubernetes container abstraction. Other times we use kind of simple Docker containers to do this stuff. But we're always running on COTS devices. We're always running on cloud services. We're always going to be consuming some kind of compute to do this job. There are no, except at the edge of the network, there are no hardware boxes in this implementation. So we do use stream muxing. We do use native CPU and core load balancing in order to achieve efficiency. And for us, if we look at kind of where we've come, for a kind of a start point, we could deal with about 200 streams per node, about 3 gigs in, 3 gigs out per instance. This is one of our lab nodes. I'll spare you the full specs of it. That's not really the important thing here because I've got the same reference to see where we've come from. So now, doing all of this load balancing and stream muxing, we're now, for those same workload, we're still 15 megabit streams. We can now deal with, at the moment, today, 600 streams, 9 gigs in, 9 gigs out on that same node. So we're now almost saturating 10 gig networking in and out of that device. And actually, the problem we've got at the moment is not one of full utilization. It's one of other application things we need to go and fix, right? So this is really good news because suddenly, for that same footprint, our customers have got 3 times the amount of firepower available to them. So how does that impact our customers? Well, it reduces instance costs for a start. If I'm doing the same workload, I can use either a smaller instance for that given workload, or I can have better utilization of my invested resource. And this absolutely impacts the bottom line on transport cost. And this is the thing we're struggling with. So this is where we need to be focused. We need to make this as cost-effective as possible for our customers to deliver. It brings better scalability. The interesting thing about not needing so much firepower is that, generally speaking, the kind of devices, the kind of compute you need is more available. You know, the public cloud have a kind of a bit of a standard deviation bell curve of the size of instances and what's available to get hold of. So you want to be somewhere in that bell curve to make sure if you're using burst capacity in public cloud, you want to know that you can burst into an instance that's going to be there and available for you. And by creating a more efficient transport mechanism, that likelihood of that happening is higher. It brings, of course, better scalability, better availability. And so we think all these things come together to create a product scenario that's really effective for the pressure our industry is under at the moment. So you need orchestration, observability, efficiency, and that scalability. So I'll spend a few minutes just wrapping up. And we need to remind ourselves that the industry is tough for a lot of businesses at the moment. Transport margins are incredibly tight, and we need to stop thinking about internet delivery, about bolting some boxes together, and we need to think about how internet transport becomes an enterprise solution to the broadcast business. So it's time to, if we need to focus, we need to innovate in efficiency and not in, let's say abstract features for transport. We need to have end-to-end orchestration for improved operability. Operators don't expect to have to bolt together hops in a transport network. They expect to press a button and route a source to a destination. And by doing that, we can preserve the use of media-centric operators. And this is important to preserving our ability to create compelling content. If it was, a bunch of IP and IT operators making content, the broadcast landscape, I think, would be quite different. We need end-to-end observability. We have to use that for improved reliability and the ability to react to when things go wrong. It's not always when things go right. Reliability, everything fails all of the time, and reliability is about how you can respond to something, not necessarily that something's not broken in the first place. We should champion efficiency above all else. This will have the biggest impact to our customers today, and we have to be able to seamlessly scale up. This area is growing rapidly, and we have to meet that change. Thank you.